Today we're going to talk about what's called one-sided limits and the concept of continuity. And this is just a general discussion to get some ideas into your brain. And in class we will work through some more detailed examples. So continuity has to do with whether or not a function has any gaps in it. For example, I have the curve right here. So let's say this is some sort of a function. And if a function is everywhere continuous, then there are no gaps. So let's say I've got my TARDIS here, and my TARDIS can ride right along this smooth curve, and it's everywhere continuous, so there are no breaks, there are no jumps, and there are no issues. So if this is a function, we can say this function f of x is continuous over this range, and I could actually put arrows at the end to say it's everywhere continuous. There are no gaps. So let's look at this guy. And he is, let's call him a function. He passes the vertical line test. Here we go, and so the TARDIS takes a ride on this guy, and all of a sudden, he falls off a cliff, and there's a big gap right there. So this is a discontinuity. Obviously, because they are not connected. And sometimes we have a discontinuity with a gap in it. That's called a jump discontinuity. We see those when we have a gap like this between the two sides. It still passes the vertical line test, though. We're going to say that this point and this point are not directly above or underneath each other. Or to make it even better, if they were, one of this would be a closed circle and the other one would be an open circle. So in this case, again, because it skips and we can't follow the track, that is a jump discontinuity. The other type of discontinuity is called a point discontinuity, and that's where we have a gap in just a single point. It's really hard to see on a graphing calculator, actually. You'd have to blow up the window pretty big to see the single point in that gap. The point discontinuity almost looks like a smooth curve. So if the TARDIS is riding along here, and he just has a single little jump to jump over, you'll see on either side of that point, the TARDIS is approaching the same value. So there's no giant gap. And these different types of discontinuities will have different limits when we talk about left hand and right hand limits. So we're going to talk about one-sided limits today. So the different discontinuities affect whether we have an overall limit at a certain point in a function. And then it also affects whether we have a left hand or right hand limit. So if I'm looking at this function here, it is a function because we have an open circle and a closed circle. We have a jump discontinuity. Well, what that means is if I'm approaching that discontinuity from the left, here's my zombie here, my walker. He ends up right up here at the top. And Daryl over here, as he approaches, he ends up way down here. So they are not at the same location, at the same Y location. So when you have a jump discontinuity like this, the two sides are approaching different Y values and they don't meet. Now if I were to look at the actual value of this function, the value of the function is the closed circle where Daryl is. So if I were evaluating the function itself, its Y value would be this closed circle here. The open circle does not have a value there. So let's look at this function. I have an open circle and then a closed value in the middle and then an open circle at the end. It's still a function because it passes the vertical line test. If I were to find the value of this function, it would be where the closed circle is. But let's think about the limit now. And we're going to break this up into a left hand and a right hand limit. If I am approaching from the left, if I'm going this way, I'm moving this way, so that's approaching from the left. That's what this zombie guy's doing, this walker. He's approaching from the left, and he's following the function up to the top. So he is approaching this high value up here. If I approach from the right, which is this arrow, and I move this way, that's Daryl. Daryl's going to ride this function approaching from the right, and he ends up down here. So they are not at the same y location, and neither one is at the value of the function. When we have something like this, we are going to define tomorrow what a left-hand limit is, which is this y value approaching from the left, and a right-hand limit, which is this y value approaching from the right. And what you can see is when they do not approach the same y location, the overall limit does not exist. So now let's look at this guy. He's a function, and he has a point discontinuity. So what a point discontinuity does is approaching from the left. I don't want to grab him, I want to grab my arrow. Approaching from the left. I'm taking my walker, and he's approaching from the left. He's showing up right there at that level. Well, what happens with Daryl approaching from the right? He's riding along, and it looks like they both are approaching the same location. Even though that single point doesn't exist in the function, they are both heading towards it. And then, you know, there's trouble. Of course, you know Daryl's going to win because Daryl always wins. But in this case, we have a left-hand limit, which is this y value. We have a right-hand limit, which happens to be the same y value because they are showing up in the same spot. So this overall limit is going to exist. So we'll finish up by putting a function on a coordinate grid. And we'll take a look at just a couple points. Let's take a look at, we're going to look at this discontinuity. We're going to look at 3 points. This guy, and this guy. So approaching from the left, my first point, if I'm riding along this function, I'm going to end up right here, which it looks like to be about negative a quarter or so. Approaching from the right, I'm riding along this function, and I end up at the same spot. It also happens to be the value of the function. So in this case, my left-hand limit is equal to my right-hand limit, which means the overall limit exists, and it's the value right here. For the next one, if I'm going to evaluate around this point, I'm approaching from the left, which means I'm riding along this function until I land at this point. It doesn't matter that the actual functional value isn't this one. The actual value of the function when x is 1 is at 3. But as I ride along, I'm approaching a value of 1 from the left. As I move from the right, I'm moving along the function, and I'm approaching a value of 1 again. So when my left-hand side and my right-hand side meet at the same point, that overall limit exists. I have a left-hand limit of 1, I have a right-hand limit of 1. Therefore, since they're the same, the overall limit exists, and it's 1. Finally, the jump discontinuity. If I'm moving from the left, I'm riding along this function, and it has a limit of 1, the left-hand limit, because I end up at a positive 1 in the y direction. If I move from the right, I'm riding along down here, and I'm way down here at negative 1. So my left-hand limit is 1, my right-hand limit is negative 1, which means the overall limit does not exist because they're not going to head to the same spot. Now, limits are typically pretty confusing when you first think about them. It's a really weird concept. It's not like normal math. But this just gives you a little introduction, and then we're going to look at it in much more detail when we get together in class.